playing movies.
And welcome to me. I accept a lot.
I didn't do assignment 5.
Oh my god!
Yeah, and it was due this
Oh
morning.
my
I was like,
god!
fuck.
It
comes up
First announcement, the material for this week is mostly not in the book. So we have a chapter on relative rate of change, it's 6.8 I believe, but mostly what we are going to do this week, elasticity of demand, such things are not in the book. There are, well, 2 pages of notes online. If you go to the main course website, you'll find supplementary notes for week 6, and you should find them and look at them. And there are also, even more important, there are suggested problems about these topics, and they are also online, so you should look for them under the same link. Okay, so the topic for, well, we'll start with a kind of rate of change, and let me remind you a little bit about, well, rate of change, instantaneous rate of change. We talked a little bit about, well, the growth model. You have, say, a country, and you have the number of people in the country. And suppose I tell you that the rate of growth of a country in a particular year is, well, 500,000 people. Is it a large amount or a small amount? Well, to be honest, it's kind of impossible question to answer. It really depends on the country. We can't compare how large it is without knowing what country we are talking about. I mean, if we are talking about some really small country, I don't know, like Luxembourg, something really, really tiny, well, then the rate of growth of 500,000 people per year is kind of huge. They probably won't fit in the country, something like this. But if we are talking about a huge country like India or China, then of course, well, it's not that huge an amount compared to the already existing population of 1 billion. So sometimes if we want to compare the rate of growth, not just in one country, well, now in the end of the year, but rather in different countries, it doesn't really make sense to talk about absolute terms. It doesn't make sense to talk about, well, 500,000 of people per year. What does make sense, makes much better sense, is what is the relative rate of change? Say, if I tell you that the rate of growth in one country is 2% per year, and another one is 1% per year, then it doesn't really matter whether one country is China and the other one is Luxembourg. Well, you still can understand that in one of them the rate of growth is larger than in the other one, in relative terms, compared to how many people already are there in the country. So we'll talk about this notion of relative rate of change. And we'll start by talking about it in general, not about a particular growth model, just rate of change of quantity. Some quantity Q, F is a function of x. Well, we know what is the usual rate of change, the instantaneous rate of change. It's just the derivative. So the question is, how fast is the quantity growing? Well, when x is x, then it's just derivative. But if I want to compare it to how large f is itself, so what is the percentage growth? I would divide this by the amount that I already have, by f of x. So this quantity is called the relative rate of change of f. Once again, it's rate of change relative to f itself. So if f describes population in a country, and the population is 1 billion and it's growing at 500,000 people per year, well, the relative rate of change is 500,000 divided by 1 billion, whatever it is, 0.5%. 0.05%. So we have this. Before we start doing examples with this, I want to tell you just a mathematical, well, kind of fact. This quantity has a different, well, we now have a different way to write the same quantity. F prime over f, if you recall, when we talked about derivative of logarithm, about logarithm differentiation, we encountered exactly the same equation. It is exactly the derivative of 1 of f. So, well, it's not a deep fact, it's just, well, a mathematical fact. This relative rate of change can also be interpreted as the absolute usual rate of change of the logarithm of f. Okay, so now let's look at some examples. Suppose that you have an equation describing population in the country, in a city. 10 to the power 7 times e to the power 0.01 t minus 2000 is the population of a city in year t. So we are given a model, and the question is, what is the relative rate of change? What is the relative rate of growth? So we are given a model of growth, and this Q describes the population in some city, and the question is how fast is the population growing, but in relative terms. So relative to the size of the city. Well, we have here a recipe how to find out the answer. We actually have two. So let me find the answer in two different ways. Use this formula first, and then I'll show that this formula also works and gives the same answer. So the first way would be, well, here's the function. Let's find first the usual rate of change. Like t. For this I'll just differentiate the derivative of, well, this number is just a constant, 10 to the power 7, 10 millions. So it's 10 to the power 7 times derivative of e to something is e to something. And from chain rule, we should also multiply by the derivative of this expression, of this argument. So it is 0.01 times derivative of t, which is 1. Okay. Then the quantity itself, let me just copy that it's 10 to the power 7 e to the power 0.01 t minus 2000s. And now I should just take the quotient. Is there something?
Is that times 0.01?
This one?
Yeah.
It's 0.01 times 1.
And what's the one?
So it's this whole thing multiplied
Okay.
by. It's multiplied by.
Okay. Okay.
So maybe like this, and then multiplied by this. Okay, now I should take the quotient. So q prime of t over q of t is the quotient. And you see that the quotient is just this number, 0.01, because this cancels out, it's just 0.01. And let's interpret this 0.01. It means that every year the population grows by 0.01 times the population, which means it is relative rate of growth of 1% per year. Well, which is very reasonable for rate of growth of city. And notice something funny is happening. The rate of growth here does not depend on the time, the relative rate of growth. The usual rate of growth does depend, but the relative one doesn't. And that's actually, well, it's just a coincidence in this case because we are given a model of growth which is exponential. So for exponential growth models, we will always have the relative rate of change will be always constant. But the absolute one is not. Okay, maybe I'll come back to this in a second, but before this, let me show you the other solution. I can do the same thing, but now apply to the second formula. I'll first find what is ln of q. So logarithm of this expression is ln of 10 to the power 7 plus, since logarithm takes products to sums, it's ln of this plus ln of this. And ln of e to the power something is just this something. So it's plus 0.01 t minus 2000s. And so the derivative of the logarithm is, well, this is just a number. It's 1 of 10 millions. It's some number. Its derivative is 0 plus 0.01. So we still get the same answer, 1% per year. So you see that, well, either way it works. Whatever, well, what you should choose is whatever looks more convenient to you. So maybe first, any questions about this simple example? Oh, so it should be clear what is this relative rate of change. It's, well, how fast is the population in this case growing relative to the size of population itself. And let me make a comment kind of to contrast such a model, exponential model of growth with usual linear model of growth. These are very important kind of models of growth, and what we see here in this example, well, first of all, what are they? Here the quantity is of this form is a constant times t to the power of some rate times t, r is some number, and here we have quantity is some constant plus some rate times t. So in one of them, the quantity increases exponentially or decreases if r is negative, and here it is increasing linearly. And what is special about this growth is relative rate of change is constant. Relative rate of change is constant. The prime over q is exactly r in this case. And here, the absolute rate of change, just instantaneous rate of change, prime is equal to R. So you should realize that here the typical growth is kind of slow. I mean, you get, every month you get a salary which is, I don't know, say $2,000 every month, and the amount of money in your bank grows by $2,000 every month. Here it's quite different. You put your money in a bank account and, well, every, say, year you get 5% interest on this amount. So then you'll get such a model of growth. The amount of money in your bank account will be growing by such a formula. And they're really different. In one of them, it's a constant amount of money, constant increase every year, and basically even in 100 years, you'll be still getting $2,000 every month. Here is different. If in 100 years you already have, I don't know, 1 million in your account, then the 5% of 1 million will be much larger, but it still will be 5%. So I just wanted to make a comment right now about the difference between linear growth and exponential one. But of course, well, these are two important models to recognize. Of course, they are not the only important models. Let's look at something different, where neither the absolute rate of change is constant nor the relative one is constant. So let's try another example. I'll have a quantity which describes population of fish in a pond. So such a function describes is the population of fish in a pond after T months. So I'm doing some experiment, introducing a new kind of fish in the pond, and well, at time t equal to 0, the amount of fish is 500 times 1 cup, so 250 fish. And as time goes by, well, the population grows by this formula. And the question is, estimate the relative rate of growth at t equal to 0 and t equal to 12 months. Okay, so we have two options. We want to estimate the relative rate of growth. We have two formulas, this one or that one. So maybe, well, which one will be more convenient for us? Second one, yes. So taking logarithm looks like it will simplify this expression, because I have a product, a quotient, and also e to some power, so it looks like logarithm will actually simplify my life. So I'll try to find logarithm of q of t. So it's ln of 500 plus ln of e to the power t minus ln of e to the power t plus 1, which is ln of 500 plus t minus ln of e to the power t plus 1. Unfortunately, I cannot simplify this expression any further. I don't have any formula for logarithm of the sum. So I have to leave it as it is and find the derivative. On the other hand, what's good is do know how to find derivatives of such expressions. So derivative of 1 of 500 is 0, because it's just a number. Derivative of t is 1. Derivative of 1 of something. Well, I'll apply the chain. Derivative of 1 is 1 over the argument, so it's 1 over e to the power t plus 1, multiplied by derivative of the argument itself. Derivative of e to t plus 1 is e to t. Perfect. Let me simplify it a little bit. It came with a minus sign. I forgot the minus sign. So please note that this should be minus. Okay, so let's simplify it a little bit. It's 1 minus e to the power t divided by e to t plus 1. Let me bring it to the common denominator. So it's 1 divided by e to the power t plus 1. Okay, so I found the relative rate of growth at any point. Now I want to find the relative rate of growth at the point t equal to 0 and t equal to 12. So q prime over q at the point t equal to 0, what is it? Well, it's 1 divided by e to the power 0 plus 1, so it's 1/2. And when we are talking about relative rate of growth, it's a good idea to interpret what does this 1/2 mean. Is it 0.5% per month? No, it's just 1/2 of population per month. It's 50% per month. So we see that in the beginning of the experiment, our population is growing rather fast. Every month it grows by about 50%. At least if during this month the rate of growth is the same in the beginning of month, then it's 50%. That's it. Okay, what happens at t, which is 12? Well, we get 1 over e to the power 12 plus 1. But what is this number? Well, I don't have a calculator, but is it a large number or a small number? Very small, yes, of course. So e is, well, it's 2.7, so it's at least 2. And 2 to the power 12 is already pretty large. It's 4096. So this number is, well, I won't tell you what it is exactly, but it is, well, smaller than, well, 1 over 1000 is 0.001, and this one is at least 5 times smaller, so 0.0002. So it is smaller than what? 0. Do I have 1 or 2 many zeros? 1 over 1000 is 1 times 100s, 1000s, divided by 5. No, it's okay. So 0.002% per month. So anyway, what I wanted to say is that this number is really, really small. Maybe it's not really important how small it is. The question wasn't really find it, just estimate. And well, what we find out, it's really, really small, much smaller than in the beginning. So this population model in a graph, it looks somewhat like this. It starts at time t equal to 0 at the level of about 200, 250. Then it grows, but then, well, you see that after a year it's almost not growing anymore. So it looks like this. There is some final level. It grows first very fast, and after some time it slows down, and then it stabilizes. So if you were to continue this graph kind of to the left, if it were meaningful, then you would have kind of such a function. So that's about how population will grow if it's restricted by, say, amount of food in the pond. If it cannot sustain a level which is larger than this, then it will reach this level and stabilize at about this level. Okay. Any questions about this? Yeah.
How did you get the percentage?
How did I get the percentage? So basically just multiply it by 100. If you have x, if the answer is x, then this 100 times x percent. Yes, you get one.
How do you take that? 0.00?
So how did I get this number? Well, I estimated that 2 to the power 12 is already about 4 thousandths. E to the power 12 is, well, larger than 5 thousandths, and 1 over 5 thousandths is what I write here. But the question was just estimate. I just wanted to show that it's really, really small. I mean, if you have a calculator, you can actually plug in the numbers and find it. Okay, so now we have a way to talk about rate of growth of basically any quantity, regardless of the absolute numbers, regardless of whether the population is growing at, I don't know, 500,000 people per year or 500,000 per year. We have a way to talk about it in relative terms. We can compare two different cities, growth in one city to growth in another one, in a kind of meaningful way. Or we can say that here the rate of growth is much faster than in there. Not only absolutely, even in relative terms. Okay, so next we'll try to apply this notion to problems from economics. And in economics, in business, well, you know how up to this point we always had problems about, well, here is a business, here is its demand equation, it was given to you, and we were supposed to analyze what is the cost, what is the profit, what is the revenue, so to find some characteristics of this business, but we never talked about, well, what does this particular demand equation tell us about the business in general? Is it a good business? Is it, well, I mean, what kind of competitors this business likely has? So we never talked about such things. But actually it is possible to compare two different businesses just looking at their demand equations and deriving some information about, well, how one of them compares to the other one. Basically, what we'll talk about is to what extent the price at which you're able to sell something. Yeah.
Just a quick question.
Yeah.
For that graph, does it mean it's an exponential function, right?
It's not an exponential function. No.
So it wouldn't have what you wrote down.
It does not have
The relative
absolute-
rate of change is not constant.
It's not constant. No.
How about the instant? It's not.
It's also not.
So it doesn't follow any of the.
No.
Okay.
So this function is not linear. A linear function is just a line, an exponential function would look like this, but this one is neither. It's like this and like this. This particular model is called logistic growth, but I mean, we are not really going into the details about particular models. Okay, so we will try to analyze kind of how consumers respond to a change in price, well, for a given product, for a product that a given business is selling. And we will try to analyze it not just for one business, but for different businesses. And for this, well, first idea would be, so the question is, how sensitive is the demand to the price? So if you increase the price, will the quantity that the consumers are willing to buy decrease by a lot or by a small amount? Okay, so first idea is like this. Let's just measure it by Q prime of P. So it sounds like it should be about what we want to talk about. I mean, this quantity is, well, like all the other marginal quantity, it reflects as the price increases by $1, how much the quantity will grow, how much it will decrease. So it looks like a reasonable quantity to talk about, but actually it isn't. What do I mean it isn't? Well, suppose I have two businesses and both sell, say, chocolate bars. But one is a small local business, it sells 500 chocolate bars every week. The other one is a huge business, it sells 5 million chocolate bars a week. Can we meaningfully compare these numbers for them? If one of them increases the price by $1, well, it will be selling 50 units less. If the other one increases the price by $1, it will be selling 500,000 units less. So it's not really meaningful to compare these numbers. It's just because, I mean, it might be that for both of them the quantity demanded decreased by 1% or by 5% or 20%. But for one of them this number is 50 chocolate bars, for the other one it's 50,000 chocolate bars. So it's not really the quantity that we want to talk about. If we want to consider businesses of different sizes, what we want to talk about is more like this, the relative change. So now this quantity is about, well, as the price increases by $1, in relative terms, how much will quantity decrease? So this quantity will reflect something about your business in the following. So if the price increases by $1, the quantity demanded will decrease by 10%. Okay, so that's a good thing, but still it's not good enough. So now using this quantity, it's meaningful thing to compare a business, a large business that sells chocolate bars, to another business, maybe smaller, maybe slightly different chocolate bars. But we really can't compare using this quantity business that sells chocolate bars and, for example, cars. Why not? Well, if I sell chocolate bars and I increase the price for a chocolate bar by $1, it's reasonable to expect that the quantity demanded will decrease by, well, something substantial. It will decrease by 10% or maybe 20%. But if I'm selling cars and I'm selling them at, I don't know, $15,000 for every car, and I increase the price by $1, well, nobody is going to notice. So this quantity is really meaningless if you wanted to compare the businesses which sell different products. If one of them has large price and the other one has small price, well, you still want to compare the characteristics of the two businesses. But this quantity is quite meaningless. What you want to do instead, you want not to increase the price by $1, but rather by 1%. And then it becomes a meaningful question. You can try to compare what happens if you increase the price for a chocolate bar by 1%, and let's say the quantity demanded decreases by 10%. And if you increase the price for the cars by 1%, and the quantity demanded decreases by, say, 5%, well, now you understand something about the qualities of these two businesses. One of them has better price control. It has more freedom in changing their prices. So we don't want to talk about this quantity. What we want to talk about instead is kind of like this. It's relative change in quantity divided by relative change in price. So if we increase the price by 1%, by how much will the quantity decrease? So it seems that this quantity is meaningful. And in fact, yes, it is. So this quantity will be called elasticity of demand. Before we actually, well, introduce this thing, let's find out the formula, how to, well, given a demand equation, how to understand this. So what is it? So suppose I'm given a demand equation. Q is a function of Q. I know how many products I will be selling at price P. So number of units sold, price P. Well, what is the relative change? Well, I should say relative rate of change as price increases, something like this. Let me say rate of change. So what is the relative rate of change? In quantity. Well, we already know we should take the derivative of the quantity, dq by dp, and divide it by the quantity itself. Maybe another way to write it is q prime over q. That's exactly what we talked about. But now we agree that that's not quite what we want. This only measures if we increase the price by $1 by, well, by what percentage will the quantity decrease? That's this amount. But that's not all the amount. We want to divide it by the relative change in price. Like how much this increase of $1 was in percentage terms. Well, how much was it? So relative rate of change in price. Well, we should apply the same logic, but now to price. So we should take price and differentiate it relative to P and divide by the price itself. So it should be dP by dP divided by price itself. Well, but what is it? What is dP by dP? 1, of course. It's like derivative of x relative to x is 1. Derivative of price relative to price is 1. So another way to interpret this is, well, in percentage terms, what does it mean to increase the price by $1? Well, it's 1 over P. So you should take this $1 and divide by the price. That's in percentage terms. In relative terms, what is this increase? And then if we divide one by the other, we get to this meaningful quantity, which we call elasticity of demand. It's this amount, Q prime over Q, divided by 1 over P. So it is P divided by Q, so P times Q prime over Q. So this quantity is exactly the same as this quantity. Okay, so let me, this was kind of motivation behind introducing this quantity. Let me now just write the formula for the quantity and give it a name. So elasticity of demand called epsilon p is given by such formula. It's p times q prime over q. We can also rewrite it in this funny way, dq by dp, to emphasize that it's, well, this derivative is relative to p. And that's a formula that we should remember. Maybe kind of aside for people who actually study economics and hear this in another course on economics, you would also write it sometimes in this way. dq over q divided by dq over p. It also works, and the meaning that you would assign to it in economics is relative change in quantity divided by relative change in price. And you see that it's kind of nice rearrangement of this formula, and it is somewhat meaningful. So it is exactly the same concept that you were introduced in economics class. But let's now talk about it in this context. So what is the meaning of this quantity? Let's interpret it. Let's interpret it in a similar way the way we interpreted marginal quantity. So say marginal cost was how much the cost increases if you increase the quantity by 1. Well, this has a similar meaning. It's just that it has the same meaning but in relative terms. So meaning. If price increases by, well, it's not by $1, it's rather by 1%. Whatever the price is, if you try to increase it by a small amount, by 1%, the quantity will change by epsilon %. So it actually has a rather familiar, well, familiar interpretation. It's exactly like marginal, but rather in relative terms. If you increase the price by 1%, how much in relative terms will the quantity change? So let's look at some examples first. First, any questions, clarifications, just on definition? Yeah. Relative rate of change in price. Yes. So the question was, what is this equation about? How to interpret this answer? Well, so here I also had kind of relative rate of change in quantity, and that was q prime over q. So let me first interpret this thing, and then I will interpret this thing. So this thing the relative rate of change in quantity. It's about if you increase the price by a small amount, say $1, and then I'm thinking about price which is larger than $1, and large price. Think about it, $10,000. So $1 is a small amount relative to the price itself. So if I increase the price by a small amount, by $1, how much will the quantity change in relative terms, in percentage terms? Okay? This thing is about the similar thing, but about the price. If I increase the price by $1 in percentage terms, how does it express? What does it tell about the increase in price? So $1 is exactly 1 over P part of the price itself. So $1 increase in price is about 1 over P percentage, well, relative increase in the price itself. So if the price is 100, then increase by $1 is exactly 1%, 1 over 100. Okay, so let's do some examples. Let me not erase this part. So if price is 10 minus Q over 100, so that's the demand equation. Find the elasticity at P equal to 2.5. Okay, so we are given a demand equation, and the question is what is the elasticity at price level of $2.5. Okay, we go to this equation and we see that we'll have to find derivative of Q relative to P, dQ by dP. So we better express this quantity as a function of price. So the solution, first step, express Q in terms of P. Well, that's rather simple. It's 100 times 10 minus P. So it's 1000 minus 100 P. Okay. Then we find the derivative of Q relative to P. In this case, it is just minus 100. Meaning that, well, an increase in price of $1 leads to a drop of demand of 100 units. Okay, but that's not what the question is asking. It asks about the relative terms. It asks about elasticity. So we should take this thing and plug it into this formula. So elasticity at price P is P divided by P times Q prime, which is Q prime divided by Q. So it is P times minus 100 divided by Q, which is 1000 minus 100 P. Is minus 100P divided by 1000 minus 100P. Okay, great. So we found this elasticity of demand at price P. Now the question itself is about price level 2.5. So we should plug in elasticity at 2.5. You'll get minus 100 times 2.5 divided by 1000 minus 100 times 2.5. So it is minus 250 divided by 750 minus 1/3. So we found this quantity minus 1/3. Let's interpret it a little. What does it mean that the elasticity is minus 1/3? First, what is this weird minus? Why would we expect a minus sign here? Second, negative slope of what? I mean, yes, there's negative slope of something, but okay, go on. Say again?
It's inelastic, but the minus is not possible.
Not possible. Okay, so, yeah?
The law of demand says that the increase in price only demand will go down, which doesn't.
Yes, exactly. So this minus sign just tells you that an increase in price will lead to its decrease in quantity. That's very logical. If you increase the price, you will naturally sell less units. So negative sign, well, it's not a bug, it's a feature of this program. So maybe let me say that elasticity is always negative. Because increase in price leads to decrease in quantity. Actually, there are some conventions, so some people, I mean, they are annoyed by this minus sign to such extent that they always talk about the absolute value of elasticity, just forget the minus sign altogether always, and, well, you'll have to, to adjust to the convention. In this course, we'll talk about negative elasticities always. If in your, say, economics or business course, you have positive elasticities, you'll have to disregard the minus sign. But anyway, okay, so we understood this minus sign. What about this 1/3? What is it about? Well, let's remember what is the meaning. It means that if you increase the price by just 1%, the demand will drop by not that much, by one third of a percent. So it means that actually the consumers are pretty much willing to suffer increase in price. I mean, for every 1% in price, only 1/3 of 1% of consumers will stop buying your product, which is okay. Now, let's look at what happens at a different price level. What is the elasticity at T, which is 7.5? Well, we have the same equation if we should just plug in 7.5. So it is minus 100 times 7.5 divided by 1000 minus 100 times 7.5. So it's minus 750 divided by 250, negative 3. So here, the situation is different altogether. If you increase the price by just 1%, the number of consumers who will stop buying your product will be 3% of the consumer base. So here, at this price point, the consumers are very, very sensitive to increase in price. If you try to increase the price by just 1%, well, already 3% will stop buying your product. So in fact, people distinguish these two situations when consumers are very sensitive to increase in price and when they are not very sensitive, and we have special words for this. Maybe before we introduce some new words, any questions about the old words, about this example? Yeah? At $10, the quantity will be what, 0. So you won't be saving anything. Hmm? Yes, so the elasticity is undefined, and the reason it's not defined is because, I mean, from $10 you already can't increase the price. Because at $10 the equation tells you will be saving 0. So you can't increase it any further. Then elasticity is not defined. Okay. Other questions? Yeah.
So, and then at that case, the -3 with the negative, like the 3% be 3% of the quantity or
Of the quantity, yes.
of the quantity, okay.
So whatever quantity you are selling at 3% at this price level, this 3% drop will be 3% of that quantity. So maybe let me interpret this explicitly. So this means that for an increase of 1% in price, it means 7.5 cents. No dollars, but rather cents. Small increase in price will lead to decrease in quantity of 3%, which is, well, 3% of whatever the quantity is. 1,000 minus 100 times 7.5. So it will be 3% of 250. So once again, the quantity that you will be selling at this price level will be 250, and increase in 1% of price, so 7.5 cents, will lead to a decrease in the quantity of 3% of this 250, which is 2.5 times 3, 7.5 units. Yeah.
How come P price is now in cents and it was in dollars before?
So this 7.5 cents is $0.075. So it is still, I mean, I wanted 1% of the price. The price itself is $7.5, and 1/100 of it, 1%, is $0.075, which is 7.5 cents.
Okay, so will it always be like an increase of 1% when you're doing elasticity? Like, because like when we did the 2.5.
So here you could take, I mean, instead of 1%, you can talk about any small change. But in relative terms, you could have talked about, say, 0.5% increase in price will lead to 3 times 0.5% decrease in quantity. That will also work. I just choose 1% because it's very convenient to multiply it by elasticity. Other questions? Okay, so let's introduce some words for this page. Then demand is very sensitive to change in price, and then it's not very sensitive. So if the elasticity is greater than 1, and I mean the absolute value of elasticity, which means the elasticity but without the minus sign. So if elasticity is greater than 1, the quantity sold is sensitive to the demand is sensitive to change in price. And we say demand is elastic. So you see that if epsilon is greater than 1, let's say 10, then what happens is that 1% of increase in price lead to 10% drop in how many products you will be selling. So this situation is called elastic demand. The opposite situation, so please leave some space here because we'll add to this. We'll have some characteristics of businesses with elastic demand. So if epsilon is smaller than 1, the demand is not really sensitive. The change in price we say the demand is inelastic. And finally, we also have a name for something in between. If epsilon is exactly -1, we say demand is unit elastic. So in this situation, 1% increase in price gets reflected in 1% decrease in quantity. So it's a situation somewhere in between. Well, let's now think, yeah.
Is that absolute value?
That's epsilon is exactly -1.
Yeah.
So the absolute value is exactly 1.
Okay.
And since epsilon is always negative, it means that epsilon is -1. Okay, so let's now think about what does it tell you about the business that its demand is, say, elastic. What does it mean about the business that if you increase the price even slightly, the consumers will stop buying the product? I mean, not altogether, but large part of consumers will stop buying the product. Well, usually it means that they have a choice. They can switch to another product and or maybe stop buying altogether. Maybe they didn't really need this product. It was kind of luxury product. Or more frequently, it is just a product for which there is a ready substitute. So for instance, if you're selling chocolate bars at, I don't know, $2 per bar, it's reasonable that your demand will be elastic. Because many companies sell chocolate bars at $2 per bar. And many consumers don't really can't tell the difference between one brand and another one. So if you increase the price by 1%, well, many consumers will just buy the other one, which didn't increase the price. So this thing happens when, so it tends to happen when there are substitutes available. So once again, if the consumers have a choice of buying your product or some other product for slightly different price, well, you don't really have that much price control over the price. You sell it whatever the consumers will be buying. If you try to increase the price, well, they will stop buying. I mean, once again, not altogether, but this quantity tells you to what extent they will stop buying. in this situation, well, suppose that epsilon is really, really small, say 0.1. It means that for every 1% increase in price, only 0.1 of consumers will stop buying. Well, what does it mean? It means that the consumers really, really need your product and they can't change it to anything else. What kind of business has this characteristic? Oh yes, yes. So daily needs, yes. So if you are selling, say, if you are a monopoly who is selling a bread, and you know that people need bread, well, and you have no competition, yes, you would be selling bread at whatever price you want, and people will still be buying bread because they need bread. But maybe even better example would be electricity, because electricity tends to be a natural monopoly. People, I mean, there is usually just one big company who is selling electricity, and people need electricity. They can't substitute it with more or less anything else. So this happens when there are no substitutes available. Which tends to happen with utilities like so basically whatever price you set, people will buy. I mean, yes, if you increase the price by a large amount, well, some people maybe will take their old light bulb and change it to a more efficient one, so the quantity will decrease a little bit, but not drastically. So there will be some decrease in quantity, but not a large one. Okay. Finally, there is another point to be told about these elasticities. Something about the revenue of a business operating at one mode or another one. If the demand is elastic or if it is inelastic, well, it has some consequences about the revenue. So let's see. If demand is elastic, meaning that the elasticity is greater than 1, then, well, let's say it like this. Increase in price will lead to, let's leave a blank here, in revenue. Which is P times Q. Now let's figure out what should I write here. Okay, yes. So here I have the revenue. Recall that the revenue is price times the quantity. What does it mean that demand is elastic? It means that for a small percentage increase in price, the percentage decrease in quantity will be even bigger. So say for 1% increase in price, the quantity will decrease by 3%. What will happen to the product in this situation? Well, it will decrease by 2%. If the price increases by 1% and the quantity decreases by 3%, the product will decrease by 2%. So here we always have a decrease. Well, we can argue similarly. So maybe let me explain it once again. if you try to raise your price, yes, you will be selling each product at a higher price. You will be getting more dollars for each unit sell. But the number of units that you sell will be much smaller, well, exactly by that extent, the elasticity. Much smaller than the increase in price. So overall, the amount of money that you will get from the sales will be smaller. If, however, demand is inelastic, like for electricity companies. So if epsilon is smaller than 1, then increase in price leads to increase in revenue. So you increase the price, and the offsetting decrease in the amount of units that you sell, well, is not nearly that bad. I mean, you increase the price by a lot, but the amount of units that you sell, well, gets smaller by just a little. So the product will still grow. And finally, what does it tell you about unit elastic demand? So if demand is unit elastic, epsilon is -1, then revenue is maximum. Why is that? Well, if it is not maximal, then it means by increasing or decreasing it, you can make it bigger. But, well, you can, in one situation, if epsilon is greater than 1, it makes sense to decrease the price. Here it makes sense to increase the price to make the revenue bigger. But here you have no choice, it's already maximum. Okay. So we found these statements rather qualitative. We just started about, well, what is the meaning of elasticity and how does it reflect. Guys, are there any questions? That's another question. Okay. Actually, there is a very important equation relating the elasticity and the revenue, which will tell you about these conclusions rather immediately. We'll try to analyze quantitatively how change in price will get reflected in the revenue. So how change B gets reflected in change of revenue B up. Well, we know what we should measure. We should measure the change in revenue relative to price. Derivative of revenue relative to price. We also know what is the revenue. Revenue is price times quantity. Okay, we want to differentiate such a product relative to price. Let's use the product. Here you have P times Q. Derivative of P relative to P is 1. So it's derivative of P, which is 1 times Q, plus P times derivative of Q. But you see, we already have here something almost like elasticity. elasticity is P Q prime divided by Q. And here we have just P Q prime. So let's rewrite it as Q x1 plus P Q prime divided by Q. So here we derive another important equation about elasticity. The change in revenue with respect to price is the quantity multiplied by 1 plus elasticity. So in particular, it tells you, well, quantity is always a positive thing. You can't sell negative amount of products. So it tells you that the sign of dr by dt is the same as sign of 1 plus epsilon. Which means that if epsilon is smaller than 1, dr by dt is positive. If epsilon is greater than 1, dr by dt is negative. And finally, epsilon is exactly minus 1, dr by dt is 0. So we get the same conclusion that we arrived at here qualitatively. We now arrive at the same conclusion quantitatively. If the demand is inelastic, then increase in price leads to increase in revenue. If the demand is elastic, increase in price leads to decrease in revenue. If the demand is unit elastic, then the revenue is already maximum. On the graph, we have such a picture. Horizontal tangent line, which means the maximum. Okay, so from this lecture you should remember the following things. What is the relative rate of change? What is elasticity of demand? What does elasticity of demand mean? And, well, basically, how does it reflect in revenue? And just a reminder, next time you have this in the